We should use the time. Okay, one thing and another record. Where is it? Here. Okay, so we know this one. We talked about this one, and you know everything in mechanics, so it's great. Okay, let's start with a perfectly useless task. Convert 68 Fahrenheit temperature value to Celsius and Kelvin. Okay, so let's go back to the lecture because I don't know this by heart. So okay, what I have in my mind, nothing. So from Celsius, I got the Fahrenheit in this formula. So I need this one. Okay, it's usually I always ask you to use the units, because if you do the calculation with units and you got a good unit, then perhaps the result is good. But now I'm perfectly disturbed what is what, so I don't use units here, but that's exceptional. So this is 4 times 9, and this is 5, so it means result is this. I'm not sure. I unfortunately made mistakes quite frequently. So the best way to do this is, okay? You find it? I don't know, but my internet is quite. Oh, I know why. Because I should have login or something like this. It's okay?
Yeah.
Great, then we we are okay. So this was the first one. Oh yes, I almost made a big mistake because I haven't finished this. So how much is it in Kelvin? Because the difference is 273 Kelvin. The Kelvin is good because, for example, when you have this gains at low, P per T or V per T or something like this, if you write Celsius, then the answer is usually wrong. You always have to use Kelvin. That's the natural temperature indicator, actually, unit, and the natural scale. It starts with 0 Kelvin, it means 0 movement. One definition of temperature is the parameter, the quantity, which is proportional. I started earlier because I don't have too much time. We converted the 1 Fahrenheit temperature to Celsius and Kelvin. That's it. You can use it with the browser passwords. So the one definition of one type of temperature is the quantity which is proportional to the energy, kinetic energy, kinetic or rotational energy of a particle, the free parameter. I mean x, y, z, or the rotation. This is one definition. So, and if you calculate what is the energy of a particle close to the 0 Kelvin or higher Kelvin, you got better fitted results. Okay. Next, an aluminum 100 kilometer long transmission line was installed at 0 Celsius. What will be its length at 40 Celsius during summer? The thermal coefficient of the aluminum material is this. Usually these thermal coefficients are quite small. So this means from 1 meter, 0.1 millimeter. No. 0.01 millimeter for 1 meter. However, if you have 100 meter, then that's 1 millimeter. If you have 200 meters, then that's 2 millimeters. And 2 millimeters displacement in concrete can count. It could be a problem. If you have metal, then these coefficients are higher. So, for example, trains must be somehow protected because the beams, the lanes would deform because of the heat. Because the heat at summer could be 80 or 90 degrees at the sun. Okay, so let's continue. You don't have problem with the math here. Okay, because a lot of Hungarians have, unfortunately. So, the first thing, you read the exercise. The second, you understand. You need to draw something. We have this aluminium, what is it, transmission line. That's 100 kilometer long, so 10 over 5 meter long. This is the temperature, because we are not in the United States, so we use system international units, always. We started earlier the practice. We finished the actual earlier. So, what we have? We have this, we understand what happened, temperature increases, and then it extends. Okay? So we need the formula. That is here. Okay, what we have? Kelvin, Kelvin. Now it has no unit, has no dimension, so the result will be meter. That's great. And what else we have? Yeah. Okay. Yeah. So this is the result. The length, because that was the question. So what is the length of this during the 40 Celsius summer, but it means nothing. That's why I did this. So it will be longer with 96 meters. It seems to be not so much, but if you see, all heating system, power plants and everything are built this. There are some stuff because of this dilatation. However, because I'm not trust myself perfectly, I do it again this with the calculator. 96 meters longer. 100,096 meters, that's that. So, generally, I think, read what is the exercise, read everything if you are in a test, draw something, write down the quantities, look in your memory or in your notes for a formula or the appropriate model, do the calculation, and then you do the calculation, check the units, and then check at least or calculate at least two different ways the results. Somehow check the results. Actually, I can do it that I made a mistake. You can also do it if you like the prison meals and that society. So you will be engineers responsible whatever you will do. It's not a joke, actually. I'm saying it's just, perhaps it's a bit weird, but okay. So we had this one. We also had the Fahrenheit, and now everything is alright. You can follow me.
Yeah.
Okay. These are actually secondary school level problems. And when you will have the modern physics, there will be quantum getting, quantum, special relativity formulas and everything, but they won't be so difficult. Because it's enough to understand the other stuff. Okay. So, no one understand, we can carry on. It was a joke from secondary school, actually, from one of my teachers. And some from other teachers, it was a guy, but it doesn't matter. Okay, next one. How much heat energy do we need to transfer to 3 kilograms of water to increase its temperature from 30 Celsius to 50 Celsius. The specific heat capacity is 4.19 times 1000 joule per kilogram per Kelvin. It was a long time ago when I knew it by heart, but everyone who had diet must know it, because there is also a non-SI unit, the calorie. So, 1 calorie is 1 kilocalorie is 4,200 joule. It's more appropriate actually for us than the horsepower. Horsepower is quite appropriate, even for cyclists. Yeah, usually a cyclist can give 2 horsepower for seconds and half horsepower for hours. If there is something more, then you should check the bike and don't drink the bottle from the bottle of the cyclist. Otherwise, you will run for 1,000 in one direction. This is actually a joke, but so we have this one. Okay. If everything goes well, next time we will be at the movie and I will have double surface. No, not double. 3 times larger area to write, because there are 3 breadboards and also there is an electric motor to move them. Doesn't matter. It's fine. So, Okay, so this is one thing that I know by heart. See? Yes, this is. Result will be Joule, so perhaps it's not so bad. It's better if I calculator. So this is the same, but it's really good. Okay? It's okay, I guess.
Isn't that a lot?
Sorry?
Isn't that a lot?
The water has high heat, specific heat capacity. It's really high. If you check with the air, the oxygen, or if you check with metals, it's much higher. That's why I told you that trick. If you got wet in the rain, it's better to remove your stuff, because it really remember the Titanic. So the main hero died because of the script, but not really that one. They were in the water. You remember?
Yeah.
The water pull out the energy, the heat from their body. Yeah. It would be more interesting if the other main hero, the woman, remove the clothes or something like this. But it's another type. But it's important. The metals, they become hot during the summer and very cold during the winter, because the specific heat capacity is lower. It's not an easy question. Why is it? So why the heat capacity of the water is so high? It's related to the structure, because the water has a connection, and it's not crystal, but some connection is between the oxygen and hydrogen between the molecules. And it is a special structure when it's liquid. It's not easy. The water is also a very interesting material itself. It's a good dissolver, good liquid. Heat capacity is high. So it is good for the life, good for heating, and a lot of things. Methane could be something similar, liquid methane.
Would you say metal has a low specific?
Sir?
Doesn't that have a low specific heat? Liquid metal. You said metal has.
No metal. methane. CH4, methane.
Oh, okay.
Sorry for my pronunciation.
Alright.
So it's in liquid form. It's also good for holding life, but I don't know the heat capacity in liquid form. Usually, if you have seen liquid air or oxygen or nitrogen, they are boiling quite quickly. And for example, you can put some liquid nitrogen on your fist, and there is no problem with at all, because it boils quickly and the heat capacity is so low. Okay. So next one.
How many exercises do we have?
For today, it's this 4, and if we have more time, we have 2 other. Okay? It's better if we do as much as possible. These are simple exercises than I did last time. We have still, how much? 45 minutes. And if we have extra time, then, okay. We can do something else. Okay. Okay. So we place a copper piece with a mass of 40 grams and temperature of 20 Celsius into 200 grams water at 80 Celsius temperature. What will be the common temperature? The specific heat capacity of copper is that one, and the specific heat capacity of water is that one. Okay. Well, I will need more time to fix this.
It's just Q1 equals Q2, isn't it?
Yes. So they will exchange the heat. Perhaps you know that, perhaps you tried. You can fix these examples with Gemini or ChatGPT AI. So why we suffer with this, doing this manually?
We have to.
No.
To solve all the questions that you have.
The main reason is to change your mind and you develop your ability. But because you will use AI, you must understand and find when the AI is wrong. Because the AI is nothing more just using the vast amount of data on the internet in structured form and select from it. It's nothing more than a special statistic right now. It's not like, what was it, Skynet or something like this, or I, the robot. And when I use AI, there is always, almost always, BS in the results. If I apply it for business or physics or anything. And you must be able to understand and see that's wrong.
He gets the numbers wrong, but if you ask-
Sorry?
Gets the numbers wrong usually, but if you ask him for the method, it's.
No, sometimes
The method is better.
sometimes it misunderstands the task or cannot fix the task or it finds something similar. But it's very, very good to generate, for example, images. Right now, I'm quite contented with it. And also corrects my beautiful English with my typical Hungarian mistakes like single and plural and other things. Okay, copper. So we put copper in water. And one is sorry?
The midterm questions.
Yes.
Like this?
Yes. For the mechanics, I had no guard time, but they had the same questions in the last year, something similar. So now here I know what to ask you. For me, I did what I enjoyed: tsunami and projectile motion and so on. But if you check the homework, the projectile motion and also the waves and everything are simpler than discussed here. And also the frictional motion. It's secondary school level, yes. Yeah, if you want, I can give you, if you're interested in actually, very interested in, I can show you something. I will send you this. There is a theoretical physics competition at the Professional University. Usually it is during the autumn. Everyone is welcome. You are very happy when you can do one example exercise per week or something like this. So they are difficult actually. I can. Oh, this is what I forgot. So that's the problem. And also that's why I don't have that.
You have to sign up for the competition.
No, this is assigned to the Wi-Fi. And this is how this. Okay, here. I will send you the link. Great.
Do you win anything? Do you win anything?
No. I was happy to do the regular job at my school. Oh, he died. Yeah. So, you like this type of programs, you can fix it. Next open, you can, everyone feel free to join. And now it has an English version. This is a physics, this is for students. This guy was the best lecturer at the University. Difficult. Okay, this is a nice. So here, when you fix it, you have to integrate, derivate, and do a lot of things, not like here. Okay. This is not thermodynamics, but you learned also dynamics. Okay, I will send you. Oh, nice, very cool. Okay. Oh, let's return to our boring exercises. So, okay, so thermodynamics. We had temperature. So, I brought down everything that I had. Wait, yes. So, this is a closed system, where the energy can come only from one material could lost some energy and the other can gain some energy. So, or so the heat can, what the water will lost, the copper will gain. This is what we know, and this is how we can start. So the without delta it also works. So I can remove the delta. But this is how it works. Let's see. C1, M1, and okay, this is the M is the copper. So the copper 20, so it will gain some energy. The other side, the water will lose some energy. Okay. So we need the temperature.
Isn't T the final temperature, or is it T2 minus T?
T is the final temperature, yes.
But then in the brackets it's T2 minus T, should it be T minus T2?
Sorry?
That's delta T, right? And
Yes.
T, like the big T is the final temperature.
Yes.
Should it be T minus T2?
Okay, you are right, but I don't want to use these absolute values. The T2, the T, will be between T1 and T2. Here, that's T is higher than T2, so this is a positive stuff. And if I use this order, this T2 minus T, this will be also a positive stuff. So the 2Q will be positive. Perhaps I'm wrong, we will figure out quite soon, after I substitute to this stuff and fix it. I will need a bit more space. Do you understand my point?
yeah.
I'm not sure whether I'm right or not, but if the calculations are good, then I'm right. Actually, not the best point is, but it works. Would you write it down? See, that's why you should use Kelvin, because this would not work in Celsius. So the result will be Kelvin. I cannot do anything, just do this calculation.
About 351.
251? You did it?
351.
300?
51.
51?
It's a bit high.
It seems to be high, but it's a table.
But then if you compare the
Just these.
Wait a moment. So this is the water just give 2 Kelvins That's weird, but I can imagine this.
There's way more water and it has way more specific heat capacity, so it's logical it would be more towards the water.
That's quite good.
Yeah, it's exactly that.
Shall I substitute and do it? Or you believe that?
No.
Okay. The explanation is very simple. There are two things. One, check C1, the specific heat, and C1 and 2. So if I write normal numbers, it's with Jesus Christ, 8 times higher than not 8. 9. How much for 10 times higher the water's specific heat coefficient than the copper. Metal and water. That's one thing. The other thing is that we have 5 times more water than copper. So this emphasizes that this result is good, and also the calculations are good, because you calculated well, and also I have the solution, just I didn't use it, and that's good. That's water. That's why you use it to cool different stuff. Okay. Well, we're progressing quite fine today. It was okay? Understood? You also understood. Here there was only one thing that was important. That is the heat come from one part of the system to the other part. Because it's a closed system. We always use models. I try to tell you what is open system and closed system. If we are here, then we can heat each other because in the class. But if I check and involve the air, that's moving. Then for the air, it's not a closed system. Well, after I shut the window, of course, but still there will be some transfer. Okay. So we still have water power. At the temperature, I don't know one word. What is this shaft? Okay. Axis. Haha, that's funny. Okay, so at temperature 20 Celsius, a steel axis, soft, with a diameter of this centimeters, needs to be fitted with an aluminum ring with an inner diameter. Yes, steel and aluminum. Steel mostly means iron. Not really, but more or less. You are not at mechanics, but there is also a subject at the university technically Budapest for engineers about the different phases and crystal structures of iron, I mean steel. How much carbon do you have in it? What other array are in it? What is the how did you cool it after made it after we made it in the forge? It's an interesting stuff. The fundamentation of our civilization. Still. Okay. Yes. This diameter. The linear thermal expansion coefficient of steel is this one, and the linear thermal expansion coefficient of aluminum is that one. What temperature should the ring to be heated to? Can you imagine this? Do you understand the process? It's quite common actually.
It's almost the same thing as the.
Like the first one, the second one.
No, the fourth one. It's almost the same. We just have to make it equal. The way to solve it is almost the same.
Yeah, we will have an equation, of course, but it's a different stuff. We don't have to deal with the heat. We have to deal with this linear expansion coefficient. Okay, so you finished, I guess. I hope I understood well the exercise. This is the task what we have to do to increase the diameter of the ring to fit. So
Sweet.
There are two ways to do this. The one way, the first way, is to take the ring, heat it, and then hammer on the shaft. That's the simplest way. The other way, which is more difficult, to heat both them. I will start the first one because that's the simplest, and then we can do it again next time if it's not what they thought. So here I need the, how much time I have? 8 minutes. Okay. Now it's the coefficient. So, T1 So ow. Here, okay, the rope diameter, but another. I'm talking about this one, and alpha delta T. And if I write this stuff here, then I need 0.003 meters divided by, divided, no. Okay, so the delta T is suggested to be this 93 Kelvin. So from 20, it should be increased to 13 Celsius.
Since we were given the temperature.
This is the case when I heat only the aluminum ring.
Or won't that, like, when you get fitted, it's exactly the same, like, size. Won't that?
It should be a bit higher temperature, of course.
Won't the aluminum increase the temperature of the shaft too, and won't that increase too?
Okay, that's the second option. So if the second option is when you heat the shaft and the aluminum ring. That's the second option. I had time for the first option because we have 1 minute, but I have a Wunderwaffe. And the task is the first case. But we will do it next time for the second case. Okay? Just for fun. For you. Okay?
But then, if this was the thing, why were we given
The other specific, to misguide the hostile agent of the rotating imperialism or something like this. I don't know. So it's not my exercise, but at least it disturbs you at the test. But we can do on other day. This is also your task to navigate the unnecessary information. Okay. So that's it today. Thank you. I stopped everything, and I will send you this author link and whatever I have. Okay, thank you very much. This was a productive and fruitful day, I guess.